If you've ever looked around at the physical world, maybe watching a baseball flying through the air or looking up at the predictable orbit of the moon and thought, yeah, reality makes perfect, logical sense, well, prepare to have your intuition completely dismantled. Today, we're taking a journey. We're stepping away from the familiar, everyday, macroscopic world we live in and crossing the threshold into the absolutely bizarre, totally mind-bending rules of the subatomic realm. We are diving into quantum mechanics.
Okay, let's dive into this. And hey, if at any point during this explainer you feel just a profound sense of confusion about how the universe operates, it's totally okay. Just remember Richard Feynman's words here. You're in excellent company. Even the brilliant founding physicists of quantum theory openly admitted that when you get down to the absolute smallest building blocks of matter, nature simply doesn't make sense to the human brain. It is, in his exact words, absurd. But it's a verifiable, mathematically precise absurdity, and we're going to unpack it together.
Section 1. The end of classical physics. To really get why things get so absurd, we first have to look at where the old rules just broke down. By the late 19th century, thanks to giants like Isaac Newton and James Clerk Maxwell, we thought we pretty much had the macro world figured out. Classical physics was highly predictable. Think of it like a ball rolling down a smooth, continuous ramp. If you know its speed and trajectory, you know exactly where it's going to land. Simple, right? But as our experimental tools got better and scientists started looking closer at how light and matter interact, those trusty old equations literally hit a brick wall. The microworld of quantum mechanics operates on a totally different system. It's probabilistic. That means we can't know for sure. We can only calculate the odds of where a particle might be. And even more shockingly, energy isn't a smooth ramp anymore. Actually, scratch that. It's more like a staircase. Energy comes in tiny, discrete, indivisible little packets called quanta, like photons of light.
Moving on to Section 2, the double-slit experiment.
Now, what's really interesting about this is the actual experiment that forced scientists to accept this weird quantized reality. It's the central paradox of quantum mechanics. The setup is so elegantly simple, yet so profound that it completely shatters our classical view of how matter behaves. To wrap our heads around this, we have to look at the ultimate identity crisis in physics. Is light a wave or is it a particle? Historically, this was incredibly confusing because early experiments seemed to contradict each other left and right. Sometimes light behaved perfectly like a continuous wave, diffracting and bending. But then, as Albert Einstein showed with the photoelectric effect, light also behaves like discrete, bullet-like particles, which we now call photons. So, which is it?
The answer, amazingly enough, is both. Seriously. This brings us to wave-particle duality, which is beautifully demonstrated by the famous double-slit experiment. Imagine shining a light through a barrier that has two tiny slits in it. If light were just particles, like little bullets, you'd naturally expect to see two distinct bands of light hit the screen in the back. But instead, you get an interference pattern. It looks kind of like a barcode of multiple bands. And that is the classic, undeniable signature of waves crashing into each other. But here is the truly staggering part. Modern scientists have turned the intensity down so low that they've fired just one single particle, one single photon or electron at a time. You'd think individual particles fired one by one would eventually just build up two separate bands, right? No way. Over time, those single isolated particles somehow randomly distribute themselves to miraculously build up that exact same wave-like interference pattern on the detector screen. It's like the particle acts like a spread-out wave of probabilities until the exact moment it hits the screen and is finally detected as a solid particle. Wild, right?
To visualize this strange dual reality, let's look at a bit of an analogy. Think of a quantum system as a sort of high-dimensional Rubik's mini-cube. Physicists call these individual possible conditions eigenstates. But here's the catch. Before we look at it, the system isn't just sitting there as one solid, solved cube. It actually exists in a crazy, complex combination of all these possibilities at the exact same time. Physicists call this state a superposition. So the quantum system exists in many complex states simultaneously. It is only when we force an interaction, like when we actually measure it, that this whole superposition collapses down into a single definitive reality.
All right, Section 3, the uncertainty principle. Let's see how this builds into our next core concept. Because particles are basically these spread-out waves of probability right up until we measure them, it completely destroys our ability to know everything about them with absolute precision. This introduces the next bizarre rule of the subatomic realm, which was formalized by Werner Heisenberg back in 1927. We call this Heisenberg's trade-off, or the uncertainty principle.
In classical mechanics, you can easily know a car's exact speed and its exact location at the exact same time, no problem. But quantum mechanics imposes a strict, unavoidable limit on our knowledge. The rule is, the more accurately you measure exactly where a particle is, the less you can possibly know about how fast it's moving, and vice versa. And it's absolutely crucial to understand here, this is not just because our microscopes are blurry or our instruments are flawed. Not at all. It is a fundamental feature of nature itself. A particle simply does not possess a simultaneously sharp position and momentum. It's just baked into the universe.
Section 4. The mystery of entanglement.
So if you thought superposition and uncertainty were strange, buckle up. We're now moving to the phenomenon that famously troubled Albert Einstein so deeply that he actually argued quantum mechanics had to be incomplete. What we're talking about is the battle between local reality and quantum non-locality. This is the phenomenon Einstein famously and kind of stubbornly dismissed as spooky action at a distance. See, in the classical world, things are local. A particle is only influenced by its immediate surroundings, and absolutely no signal can travel faster than the speed of light. That's a golden rule. But quantum mechanics allows for this thing called entanglement. When two particles share a history and become entangled, their properties become mathematically linked. According to Bell's theorem, if you separate these two entangled particles, literally even by billions of light years, and you measure the spin of one, you instantly with 100% certainty predict the spin of the other. Instantly. The correlation happens without any delay, seemingly defying the speed of light entirely. They just aren't two separate things anymore. They are one single spread-out quantum system.
And finally, Section 5, Quantum Tech in Real Life.
So the crucial point I want to make here is, this isn't just abstract mathematics. It's not just philosophical thought experiments being debated by folks in lab coats. As completely detached from everyday logic as quantum mechanics sounds, these exact bizarre rules are actively powering the modern world around us. For instance, that laser pointer you use in a presentation, it relies entirely on the fact that atoms emit light at very specific, discrete spectral energy levels. Or how about the USB flash drive in your pocket? That relies on a crazy phenomenon called quantum tunneling. Remember how we said particles act like probability waves? Well, that means there's a tiny, tiny probability that an electron can just teleport or tunnel straight through a solid physical barrier. That exact quantum effect is literally what's used to erase the memory cells in your flash drive. And transistors, the tiny building blocks of literally every computer, phone, and digital screen on Earth, are built entirely on the quantum mechanical properties of semiconductors.
And this next example brilliantly illustrates the real-world power of quantum theory, the MRI machine. Magnetic resonance imaging is a life-saving medical tool, right? Well, it's essentially just a giant quantum mechanics scanner. Here's how it works. First off, the human body is mostly water, which means we are full of hydrogen atoms. The MRI's incredibly powerful magnetic field forces the nuclei of these hydrogen protons, which basically act like tiny little quantum magnets, to align. Next, a specific radio frequency is pulsed in to disrupt these quantum spin states, pushing them up into a higher energy state. Finally, when that pulse is turned off, the protons relax back down to their original state and they release energy. The machine captures this precise, discrete energy release and maps it into a high-resolution image of the soft tissues inside your body. It is literally quantum physics saving lives every single day.
Which brings us to our final thought. We started out with Richard Feynman telling us that nature is absurd. But as you've seen, that absurdity, the wave-particle duality, the uncertainty, that spooky entanglement, is exactly what holds our entire universe together and powers our most advanced technologies. So you have to ask yourself, if the predictable, solid macro world we walk around in every day is entirely generated by this probabilistic, microscopic weirdness, what does that say about the true nature of reality itself? It's a massive question. It's the kind of thing that keeps physicists awake at night. And hopefully, it leaves you eager to keep questioning the universe around you.